I'd like to demonstrate how to use variadic templates and C++ fold expressions from modern C++, C++ 17 and 20 to make what's called a compiled switch. Similar to a switch statement, it will select between different choices or different elements that may have a predefined type. It's common in event sourcing applications such as market data listeners and financial applications to listen to a sequence of events and respond to them and handle them in some way. So you would want to provide multiple handlers. And frequently, this is the main loop or the main hotspot of a program of this nature. So it might be useful in your program to compile that and have the handling kind of built in at compile time versus operating a lookup table at runtime. This is also going to be a good example of using modern C++ for lambdas and encoding tuples. I have here your standard Hello World C++ application. I just did that so that it's ready to build and that when I hit build, everything will work properly. Just for example purposes, I'm going to use the anonymous namespace. And let's just create two handlers that would represent the case of an application that's going to be handling different events as they're passed through. And some of these names and things might be a little bit contrived, but you can tune that to your application. And currently this is stateless, so we can call it const. And you can also notice that in the way that I'm going to be implementing these handlers, I'm not going to be compelled to derive each handler from the same class, as would have been done in historic times using a lookup table or a table of pointers to these classes where you would have to create some base class where you derive everything. I'm not going to do that in this case. Okay, so we have two event handlers. Let's imagine we have a sequence of events and we're going to call them. In this case, I'm just going to say we're going to call each one just to show that it works. So we want to implement this method eval indexed, and we're just going to pass it each of these types. And the idea behind the eval indexed function, or I call it a method, but really a function, is that it's going to be deciding if this value is 0, it should call for element 1, and if this value is 1, it should call for element 2. And we should be able to determine that. So this is your switch statement, essentially. So let's implement our first template. And this is going to be using a variadic template. So we want to have this list of types, right, that I just specified. And I'm going to be using this syntax to indicate that we can have some arbitrary return type in our handler. In this case, you can see my handler already returns a bool, which is something that you might use to indicate was handling successful or not. And then here's each of the types. Okay, and then, so what's my strategy going to be? My strategy is that I'm going to have, so I have this index that I'm using to choose, that's the determining factor. And what I want to do is I want to convert all of these types to a tuple. And so what basically my strategy is, I can forward each of these into a tuple, or a tuple of references to these objects themselves. And then I can use the C++ index sequence to make essentially a list of, or basically an index sequence, which behaves similar to a list or an array. That's just basically a count or a number of each of these elements, so that I can compare in a folding expression this index with the element itself. And once we've done that, we essentially will have completed the compiled switch. So we need something that's going to eval each of these things. Let's just call it eval table. Kind of comparing it here with a lookup table. And the way that this is going to get compiled in C++ is each of those paths is essentially going to get built into that function using these templates. And I'm just going to forward each of these arguments, and I just want them the same way as they came in, because, you know, essentially this is like a wrapper function. And I would like a sequence for each of these types that represents essentially their integer type. Okay, and I'm going to need some header files. So we're working with tuples. I'm going to use isTrivial as part of the example in a minute. So I'm going to grab that. Okay. So let's implement these working backwards, this eval table operation. So here's the index sequence. And once again, I'm leaving the determination of the return type to the handler itself. And I'll talk more about that in a second. And that index sequence 4 just simply returns an index sequence. All right, so that should be the expression for that method that I am wanting to implement. And basically, I'm kind of just decomposing this each step by step. What I want to do now is I want to take each of these values and I want to call a sort of decomposing function that's basically going to use a C++ folding expression to take each one of those and evaluate to the answer. And obviously each one of these could be folded in, and I've seen examples go both ways, and I'll play with it a little bit. I actually want to use a C++20 at the very end, C++20 immediate lambda to kind of fold this in, but in my opinion, it's less clear and readable than this way I'm doing it with the separate functions. So let's provide the index. Let's provide that particular value of the sequence, because that's what we're going to use to compare. And here's our lambda expression, which is going to get the answer, essentially, evaluate the result. And let's just call the method that gets the answer, let's just call it switch operation. You can call it anything you want that's relevant to your code. And now, remember, we stuffed it into a tuple, so we have to grab what's in the tuple. And then, just because it's like in the top of my mind, let's implement the switch operation first. We still need to do this eval each folding operation as well, but that's like requires a little bit of discussion. So I'm going to do it next. And let's just use standard is trivial t as an example. And I'm currently passing in that argument. I'm not using it, so I'm just going to tell the compiler I'm not interested in that particular parameter right now. But in the second, we'll fix that. That's not part of our solution that we're working towards. Okay, and then let's do the folding operation. And here's the function that we're going to call is the lambda that we passed in on each argument. So for a particular index, we're going to fold the sequence and call the function and try to return the value. Now, I want to use a folding expression. So a folding expression looks like this. It has something and then an operator, and you basically just say ... to apply it to the entire sequence on the right side, and on the left side I have to do something, and it's going to grab that value depending on the operator that I choose. So here what I wanted to do was evaluate each of these function calls, right? So let's say if the ith member is identical to the sequence, meaning this is the index, right? The index that we passed in. Then let's call the function. Otherwise, let's return 0. And in this case, why don't we call 0 false? In this case, I have a Boolean, right? So Boolean type. So all of these sequences will be false unless the index matches, in which case it'll return to the, evaluate to the result. And in that way, it would return the proper truth value. You could also use this like as an integer value with a bitwise OR. You know, sometimes this this OR might be a little bit confusing. There's some other ways you could do this operation. You could create an initializer list, or you evaluate each of these in the initializer list, and then if this is true, assign a return value here, and then return that return value. That method, you know, it's a little bit ugly because it has this nested assignment that you're not necessarily expecting to happen as a side effect of this folding expression. So I'm just going to go ahead and do it this way. This kind of forces your hand, even though you've returned an arbitrary type, down to a Boolean here, which, you know, it's so common for these handlers to return either a bool or a void. I don't see this as like a major constraint, but you know, it depends on your particular application. Okay. And then I haven't used this result at all. I'm just realizing. So we want to say, you know, if it's true, basically that the handler worked. So let's see what happens if we compile it. Okay, seems reasonable that there might be some errors. Let's see what I did wrong. It's having some trouble with the evaluating the order of operations there. I think I just messed that up. Okay, and that looks like I'm missing a semicolon. And here it looks like I've messed up my typing. Okay, I want to forward each of those, and that's the type for the forward. Okay. Get my parentheses right. Well, I horribly botched that line. Okay, and now it's building. Now remember, for our switch operation, I didn't do anything relevant to these handlers yet. I just did is trivial for this type. So what happens when we run it? So it says the handler worked. It's not very useful if I don't put a new line. So let's do it again. All right, so each of the handlers worked, right? Because it said, is this type trivial? Yes, it's trivial. But let's actually invoke the handler rather than just ignore it and do another example. So t.handle, let's return that instead. So in this case, I would expect it to invoke each of these handlers for the particular case. And there we have it. So you can see that when the index is 0, it's calling isElement1 and printing that out and returning true. It says it worked. And for the index equal to 1, it's calling the second one. So this is essentially a compiled switch. And that, the video could stop here. Just want to give like one additional bit of fun C++ magic. So now we can use an immediate lambda in C++20. So let's see if we can get this right. Let's just fold this in as a lambda. So I want to convert that to a lambda expression. Now, one of the reasons why this is super ugly is because I can't use these same template arguments because now I'm shadowing those. So we're going to have to change this. I definitely don't prefer that. We can provide the same implementation. And then simply invoke it immediately. It's a bit ugly. Did that work? Let's see. It didn't work. Why didn't it work? It didn't work because my replacement failed. for these nested types. So let's try again. This is the problem with trying to inline that stuff. Not only is it ugly, but it's kind of leads to some not nice code that we're going to have to like troubleshoot. All right. So let's see if that one works too. So it did. So I was able to build. So this is using a C++20 style Lambda. So if you prefer to have fewer actual functions involved, maybe this is something that's going to be in a header file and you want to kind of like have more inlining. This achieves that, although I think at great cost to the readability of your code. So this is a compiled switch, which is a useful expression when you want to build parsers or event handlers or any of that kind of code. Rather than having a jump table at runtime with a map of pointers, you could actually just compile it in using arbitrary types.